Hi everyone, thank you for your patience. Here are the solutions for the practice exam. The angle 280 degrees. Start with the initial ray. Positive direction 90, 180, 270. About 10 more degrees gets us to 280. This little guy is 10 more degrees. The complement, which is the reference angle, is 80 degrees. The reference angle always positive, always to the horizontal, never to the vertical, even if the vertical is closer, always up to the x-axis. This, notice I put an arrow on the initial ray, the terminal ray, and this direction arrow on the angle itself. Two angles, one positive, one negative, that are coterminal. We're looking for angles that end in the same place. So 80-degree reference angle in quadrant 4. If you go in the negative direction, you hit one right away, minus 80 degrees. If you go in the positive direction, you're looking at, you go this way, you hit one here, but that's 280. We already used that, so we'll go around again to here. There's my next angle, positive direction with that terminal ray. That would be 280 plus 1 times 360. And that's 640 degrees, and of course I could use 2 times 360 to get 1,000, or 3 times 360 to get 1360, and so on. Every integral multiple of 360 from here on out would give me an angle that ends in the same terminal ray, and the same thing is true in the negative direction. The next one would be negative 440, and so on. These are just the easiest two, but not the only two. All right, next question. Are they, is true or false, all angles coterminal with 280 have the same trig values, trig function values? This is absolutely true. The reason it's true is because alpha is the same and the quadrant's the same. If we know alpha and we know the quadrant, then we know the trig functions, right? Regardless of what angle it is, how we got to that terminal ray. If alpha is the same and the quadrant's the same, another way of saying it is the same terminal ray. Coterminal angles have the same terminal ray, so they're going to have the same alpha, the same quadrant. Or yet another way, you could say this. You could say this. You don't have to say all of them. These are ors. Or this. Or you could, some people would say that x comma y, the point and the distance from that point to the origin, could be the same, depending on what point we choose. And if we pick a different point on the same terminal ray, everything will scale so that the ratios y over r, x over r, and y over x would be the same. So no matter how you slice it, you're going to get the same trig functions if you end up on the same terminal ray. We already marked the reference angle. It's 80 degrees. Secant 280, if any trig function of any angle, again, is the same thing as is equal to that same trig function on its reference angle, except for a possible change in sign, the plus minus sign. It could be plus or minus, we're not sure yet because we haven't explored the quadrant, but in terms of magnitude, absolute value, it's going to be the same. The secant is defined as 1 over the cosine, so we can actually write it that way. Secant of 280 is 1 over the cosine of 80. Now we can investigate the sine. We're in quadrant 4. In quadrant 4, the x values are positive and the y values are negative. So the cosine is, that's supposed to be a positive sign. I don't know what that looks like. The cosine is positive, the sine is negative. So the cosine being positive means I could put a positive here, and you can leave it there if you like, but you don't really need it because it's positive by default. And there's your secant 280 can be written as 1 over the cosine of 80. That's a trig function in terms of its reference angle. In terms of a trig function of its reference angle. Negative 90 degrees starts at the positive x-axis, as do all of our central directed angles. Here's my initial ray. Go 90 degrees this way. I end up down here. And I'm supposed to pick a point anywhere on this terminal ray I choose. It doesn't matter where we pick it. Most of the time from here on out we're going to pick 1 because we know about the unit circle now. But let's say I picked 0, -4. That's certainly on that negative y-axis, or that terminal array. It is 4 units away from the origin. So this is, there's x, there's y, and there's r. So sine of -90 degrees would be y over r, which gives me -4 over 4, or -1. The cosine of -90 degrees is x over r, which is 0 over 4, which is 0. And the tangent of -90 degrees is y over x, which in this case is -4 over 0, which is undefined. You can't divide by 0. Remember that 4 over 0 is undefined, whereas 0 over 4 is just 0. You can divide into 0, you cannot divide by 0. The cosecant, the secant, and the cotangent of -90 degrees are just the reciprocals of those 3 values. So the reciprocal of -1 is 1 over -1, which is just -1. 1 over 0 is undefined. And this thing actually started out as -4 over 0. So when I flip it, I get 0 over -4, which is 0. So there are your 6 trig functions. -1 is the sine, 0 is the cosine, the tangent's undefined, the cosecant -1, the secant is undefined, and the cotangent is 0. Moving on to -210. This one is not a quadrantal angle. It's going to end in the middle of a quadrant, so we're going to have to use either the point on the terminal array. We'll find the point on the terminal array by using the reference angle and the trig functions of the equivalent first quadrant angle. So -210, we start as we always do on the positive x-axis. We go this way. That's 180. So we need 30 more. So a third of the way into quadrant 2. That's the angle theta equals -210. This right here is its reference angle, and that's 30 degrees. There's 30 degrees back to the horizontal at 180. So the trig functions of -10, we're in quadrant 2 here, where the x values are negative and the y values are positive. So this is cosine, remember. This is sine. So the sine of -210, we get the magnitude from the sine of 30, which is 1/2. That's a half. And then we get this SIGN from the quadrant. Sines are above the x-axis, y's are above the x-axis, so it's going to be positive. The cosine of -210, notice cosine of -210 is the x over r, it's the cosine of 30 degrees, which is square root of 3 over 2. And it's negative. It's to the left of the y-axis, so that's a negative. And the tangent of -210, again, we use the equivalent ratios in quadrant 1 for 30 degrees. So the tangent of 30 we learned in unit 1 is root 3 over 3. And that's going to be negative because it's a positive divided by a negative. So the tangent's going to be a positive over a negative, which is a negative. The reciprocals are familiar again from unit 1. This is 2 root 3 over 3. The first one was 2, and the last one is 3 over root 3, which rationalizes to root 3. When I flip the fraction, the sign doesn't change, so the sign carries over when you go to reciprocals without change. And this one's called the cosecant, this one's called the secant, this one's called the cotangent. And I'll leave the -210 out in the interest of time. There it is. There are my 6 trig functions of -210. Here, this is a first unit problem combined with a second unit problem. So here we're talking about, first we're talking about the magnitude. We did this in unit 1 when life was all in quadrant 1. So we're not talking about central directed angles. We can just look at the equivalent right triangle, this angle being alpha, the reference angle for theta. It may not be the same angle. It may be in a different quadrant. It may have gone around the system a half dozen times. Doesn't matter. All that matters is that we're going to find the point of the terminal array using that same reference angle. Adjacent to alpha is 1. The hypotenuse across the horizontal is 4. This side we don't know. We compute it using the Pythagorean theorem. So y squared is equal to the square root of 15. This is root 15. Now we have all the numbers we need to generate the trig function, the magnitudes thereof, but we have to adjust those for the quadrant, which gives us the SIGN, whether it's to the left or right of 0. And this is the unit 2. This is what's new, so don't forget to do this, because this is really all that's new for this unit. Every year I have somebody who says, I got everything right but the sign, and I have to inform them that there really wasn't anything to the second union but the sign, so you really do have to get the sign right. The cosine here is positive. That means it's to the x is to the right of the y-axis, so that means these two quadrants are in play. The tangent is negative, so tangent is negative. So we know that the tangent's negative in quadrants where y and x have opposite signs. This one's positive over positive, so it's going to be positive. This guy is negative over a negative, so it's going to be positive. But here we have a positive over a negative, so this is negative. And here we have a negative over a positive, so this one's negative. When the signs are mixed, the tangent is mixed. So this is the quadrant we're in here. We're in quadrant 4, sorry, because that's the quadrant, that only quadrant that satisfies the condition that the cosine positive and the tangent is negative. So we put all this together now to write down our trig functions. The sine of theta, whatever the heck theta is, we don't even know. All we know is what its reference angle is, roughly, there's alpha, so the opposite side is root 15. There's the hypotenuse, so it's root 15 over 4, and this piece here tells me that the sine is going to be negative, right? It's got to be in quadrant. It's got to be negative in quadrant 4. The cosine of theta is adjacent over hypotenuse 1 over 4, and the cosine in quadrant 4 is positive, so we get a fourth, as we should, because that's what the problem told us we should get. And the tangent of theta is y over x. That is root 15 over 1, which is just straight up root 15. And then again, since we're in quadrant 4, the tangent is negative. So that's negative root 15. Then we look at reciprocals. This one, when we flip, is going to be 4 over root 15, which rationalizes to 4 root 15 over 15. This one rationalizes to, this was just 4. And this one rationalizes, 1 over root 15 is the same as root 15 over 15. And the sine is negative, sine is positive. These are both positive, and this one is negative. This one's the cosecant, this one's the secant, this one's the cotangent. And again, I'm going to leave the parentheses of the value out here. All right, and moving on. Moving number 6. Convert to radians. So what you want to think about here in your mind's eye is here's a circle with radius 1. It's the circumference of this thing is 2 pi r, which is 2 pi times 1, since the radius is 1. So all the way around this thing is 2 pi, so that right there is pi. This length right here on a circle of radius 1 is about 3.14 units long. So if that's an inch, this would be 3.14 inches if I straightened it out and laid it down and measured it. So pi is the same thing as 180 degrees, a straight angle. So pi equals 180 is all you really need to remember. To find the first one, we just divide by 3. 180 over 3 is 60. So in radians, that's pi over 3 units. The length of that arc right there is pi over 3 radians. That length right there is pi over 3. It's a third of pi. 240, easiest way to handle 240 is just to remember that, put it in terms of angle that you know, it's an easy multiple of 60. So always try to write these as a multiple of 30, 45, 60, 90, something that you already know that's easy to come up with. This is 4 times pi over 3, which is typically written as 4 pi over 3, although it doesn't have to be. You could leave it like that if you like. So there are those two answers. And then this guy here is a little trickier. You have to recognize 510. The easiest way to recognize this is that 3 times 17 equals 51. If you recognize that, then it's pretty easy to jump to 30 times 17 equals 510. Just add a 0. If you don't, well, let's finish it this way first. So it's 17 30s. That's 17 times 30 degrees, which is 17 times, how do I get 30 degrees? Well, 30 degrees is a sixth of pi. So to get to 30 from 180, to get to 30 from 180, I divide by 6. So if I divide pi by 6, I get 100. I get the equivalent of 30 degrees in radians. So this is 17 times pi over 6, otherwise known as 17 pi over 6. You could just as easily, if you don't recognize 510 as a nice multiple of 30 right off the bat, you can always use the conversion formula, which would be take the angle in degrees, 510 times the angle in radians, pi radians for every 180 degrees. And simplify this beast. When you simplify, you're going to get that, because there are you can take 17 30s out of 51, and you can take 6 30s out of 180. Divide top and bottom by 30, and you got that. This is going to go out. It's going to be units are going to be radians. You get 51 over 18. This divide this thing by 3, you get 17. Divide this thing by 3, you get 6, and so on. So you just have to, if you use the conversion formula, you end up having to do a lot of canceling, but it's not wrong. Convert to degrees. So pi over 2, just think that's 180 over 2, which is 90 degrees. This guy a little trickier. It's minus 7 times pi over 3, which is minus 7 times 60 degrees. Pi over 3 is 60 degrees. And so this is equal to 7 times 6 is 42, so it's minus 420 degrees. That should be a minus sign. That's the easiest way to get that guy. 10 pi is just 10 times 180 degrees, because pi is 180. That gets you 1800 degrees. Alright, so don't forget there are 3 parts here. So the first part is to draw and label the indicated arc. So 11 pi over 6, we're dividing, this is minus 11 times pi over 6, which is minus 11 times 30. If you're thinking in terms of degrees. So 1, we're going this way, it's positive. No, it's negative, sorry. Negative. So we got to go this way. So that's 30, 60, 90. It takes 3 of them to get 90. And then 4, 5, 6, takes 6 of them to get 180. 7, 8, 9, takes 9 of them to get up to 270. And then 10, 11. So that's 300 degrees. It's 30 degrees short of being all of 360. But we're not thinking in terms of degrees anymore. We're thinking of arc length. So we send our PE student running along the circular track at this point right here. And we keep yelling out, "Where are you? Where are you?" When they get to here, they stop and we yell out, "Where are you?" And you respond, "I'm at square root of 3 over 2 comma 1/2. How did I get that? Well, because if I draw a radius here of length 1 and drop a perpendicular down to the x-axis, that's 30 degrees, because we're 30 degrees short of 360. So I'm looking at a 30, 60, 90 right triangle. This side would be root 3 over 2. That side would be a half, since I have 1 on the hypotenuse. So to find a coordinate point, you go out x units, which is square root of 3 over 2 units, and up a half unit. That's where this is coming from. So now I've drawn and labeled the arc. I should label it. S is the arc. It's this path, highlighted in blue. The label, the coordinates of the point, I did that right here. Maybe I should use a different color to make sure you realize that there's 3 things required each time. And the last thing is to come up with the value of the trig function. So don't give me 11 pi over 6. That's just that's the arc length. I want to know what the tan of 11 pi over 6 is. Tan of minus 11 pi over 6 is equal to the y over x coordinate. Tangent is y over x. So we just look at these guys. It's a half over the square root of 3 over 2. They're both positives. The tangent's going to be positive, and we've simplified this enough times to know that's 1 over root 3, which rationalizes to root 3 over 3. That's the third piece. Again, I should use a different color, so you know it's not just one problem. One part is 3. This is root 3 over 3. There, and that arc right there. Those are the three things you need to complete the answer. So 3 pi over 4 is 3 times pi over 4, which is 3 times 45 degrees. So we look at the circle. We start here. That's half of 90. That's 145. 2 45s, 3 45s in the positive direction. So that's my arc S. That's the first thing you're asked for. The second thing you're asked for, the coordinates of that point. Well, to find that, draw a radius here, drop a perpendicular. That's 45 degrees. That's 1. So that's root 2 over 2, and that's root 2 over 2, which makes the coordinates of this point here negative root 2 over 2 in the negative direction, negative root 2 over 2, and then positive root 2 over 2 in the positive direction. That's the coordinate of this point here at the end of that arc length of that arc of length 3 pi over 4. And the cosine is just the x coordinate. It's this guy right here, the x coordinate of the pair. That's negative root 2 over 2. We're on the unit circle now, so the x coordinate, you don't have to divide by r anymore. If you divide it by r, you'd get 1 anyway. So notice it's a point on the terminal ray, but we're thinking of it now as not a point on the terminal ray, but the actual x coordinate of that point. That's what's new on one of the things that's new on the unit circle. And lastly, we have minus 4 pi over 3. Easiest way to think about this is minus 4 times pi over 3, which is minus 4 times 60 degrees. They're going this direction. 60 degrees would be about there, 2/3 of the way to 90. The next 60 is over here at 120, so we skip the vertical y-axis. The negative y-axis is not a multiple of 60. 3 60s gets us to 180. The fourth 60 is up here, so this is the point we're interested in, and that is the path. This is the path. There's your arc, and its length is S, and it ends here. And the coordinates at this point, to find those, again, we drop a radius there. That's of length 1, drop a perpendicular. That angle there is 60, because it's 60 degrees beyond 180. So that's 60, and this guy then would be root 3 over 2. That guy's a half, so this is, go to the right 1/2, that's negative 1/2, and then you go up square root of 3 over 2, so the y coordinate is positive. The cosecant is 1 over the sine, so it's the same thing as 1 over y. So this is 1 over y, which is right here. There's y. So it's 1 over the square root of 3 over 2, which is 2 over the square root of 3, which simplifies to 2 root 3 over 3, and it is positive because it's y is positive in quadrant 3. Yes. There's your answer. All right, moving on to 9. To show this points on the unit circle, the first thing you have to think about is what kind of number 2/5 is as a decimal. That's negative 0.4. If you think of 2/5 as 4 over 10, I think it's obvious that 4 over 10 is 0.4. So negative 2/5 is negative 0.4. So if I scroll down and look at the circle, it's an x coordinate, right? It's this is the x coordinate here. That's the y coordinate. So I go down to the x-axis, which is the horizontal axis. There's the origin. Positive numbers this way, negative numbers that way. So I go negative 0.4, that gets me right here. So I'm interested in all the points on the coordinate plane that have two things in common. Number one, they're on the line y equals negative 0.4. I'm sorry, x equals negative 0.4. They have an x coordinate of negative 0.4, and I want the ones that are on the unit circle. So that one and that one. There are 2 points on the coordinate plane that have a coordinate of negative 0.4 in the x dimension and lie on the unit circle. So we've got it down to 2 points now. And if you go back up here and look at this number, root 21 over 5, is greater than 0. That's a positive number for y. If it's a positive number for y, that means I must be going this way on the y-axis, which means it can't be that point. It has to be this point. This is the point B right here. That's the point I'm looking for. So how do I know the point B is on the unit circle? How do I know that root 21 over 5 is the correct y coordinate? Well, you can either remember that sine squared plus cosine squared plus sine squared equals 1, or you can fall back on the triangle here. That's a radius on a unit circle, so that's 1. This length right here is 2/5. You don't have to worry about the negative because it's a length of a triangle side in this context, so it's just positive 2/5. And then figure out what y is. Y would be the short side, the long leg that gets us to a right triangle. So we can just use the Pythagorean theorem. So x squared plus y squared is equal to 1. So 2/5 squared plus y squared is equal to 1. By the way, this is equivalent to cosine squared plus sine squared equals 1 if you prefer. This is 4 over 25 plus y squared is equal to 1, which I'm going to write as 25 over 25. So that should be squared. 1 squared is 1, and 1 can be written as 25 over 25. So y squared is equal to 25 over 25 minus 4 over 25, which is 21 over 25. And so y is equal to the positive or negative square root of 21 over 5. And I can ignore the negative again because it's a distance along, it's a side of a triangle. So this is correct. That means that this guy right here is correct, and this point is in fact on the unit circle. So we've showed that it's on the unit circle. We've plotted the point B, and then to mark the arc length, we start at point 0, and we move in the clockwise direction. So clocks go this way, so we go the long way around the circle, following the path of the circle. This is an arc. And we don't know what the length of the arc is actually. It's not going to be nice in terms of pi because it's not a 60-degree angle or a 30-degree angle or a 45. So we don't know what it is, but it's some arc that we're supposed to mark S. And the value of sine S then is just the y coordinate of this point. So this is negative 2/5 square root of 21 over 5. So this number right here is the actual y value. I'm just trying to rewrite these numbers up here. Negative 2/5 root 21 over 5. That's not exactly legible there, but that's what that is. So the sine of S is the y coordinate at that point is positive root 21 over 5. You don't have to divide by r anymore again because we're on the unit circle, and it's just the y coordinate at that point because we're dividing by 1. The cotangent of S, cotangent is x over y. So you just take the x coordinate, which is minus 2/5, and divide it by the y coordinate, which is root 21 over 5. And that to carry out that division, you just invert the denominator, and these go out, and you're left with minus 2 over root 21, and that becomes minus 2 root 21 over 21. It should be negative. You're in the second quadrant. When the second quadrant, x and y have different signs, so their ratios will be negative. Okay, it's kind of easier to do B on this one before you do A. Find the angle. So we know that S equals r theta. To find an arc length on a circle, we take the equivalent arc length on the unit circle. Remember, radians is the arc length on a unit circle for a particular angle, and multiply it by r, the size of the circle. Essentially, you scale up the so if you have, here's a unit circle here, and say that's theta right there, then any bigger circle like this or smaller this arc length here is going to be r times bigger than this one here. This is the arc length on the unit circle equivalent, and this is the arc length on the circle of radius r. So you just scale it up by r, once you know how long this is, you can get any other radius just by scaling by r. So that's where this formula comes from, and we're told that 3 is equal to 4 theta. Just plug in these two values to solve for theta. So theta is equal to 3/4. Notice theta is not, it's in radians, but it's not a multiple of pi, so you have to think a little bit about what kind of number 3/4 is in order to draw this. So 3/4 is a number between 0 and 1. We know that 1 radian is approximately 60 degrees, right? It's the length of one radius. So this is length of one radius, 3/4 of a radius, sorry, on a unit circle. So, or actually not on a circle of any radius. So here's the radius here. And so if we pick that radius up, if we pick this radius up and draw it on the circle, we'd get around 60 degrees. That would be one radius. But we don't want the whole thing. We just want 3/4 of it. So the sector is going to look roughly like that's about 3/4. So you can do it this way also if you like. 3/4 of a radian is about 45 degrees. So obviously I can't expect you to be precise about this, but it should look roughly like that. In other words, that's more or less what the sector looks like. This is the radius 4 here. This is the arc length 3. And now we know that if you go onto the unit circle in here, this arc length right here on the unit circle, if that's 1, this arc length here is 3/4. That's what the sector looks like. In the area, there's a couple different ways to find the area. The easiest way is just 1/2 r squared theta. That's the formula we used. So area is equal to 1/2 times the radius squared. The radius of the circle is 4 squared times theta, which we now know to be 3/4. That gives me, scroll up a little and try to keep the picture. There we go. That's 16 over 2. Well, let's just write it all out here. You got a 16 on top, you got a 3 on top, you have a 2 on the bottom and a 4 on the bottom. So that gives me 4. So you get 12, and this gives me 2. So that's 6. So the area is 6 by the formula. The other way of doing it, which is a little trickier but gives you a better idea of where this formula comes from, is if you just take the area of the whole circle. That's easy. The area of a circle is pi r squared. So it's pi times the radius of this circle is 4. So it's pi times 4. So it's 16 pi. That's the whole area here. This entire circle has area 16 pi. And so this little piece of it, how do I figure out how much of the entire whole that little sector is that piece? Well, its percentage of the whole is, its arc length is, its radians measure is 3/4, and the radian measure for the entire circle is 2 pi. So this fraction gives me the percentage of the whole that sector represents. So we take that percentage of the whole, or proportion of the whole I should say, and multiply it by the total area, 16 pi. That's basically what this formula is doing. So even if you forget the formula, you can still do this kind of calculation. This should be obvious to you as the proportion of the whole, because 2 pi is the entire circle and 3/4 is the radian measure of the sector. So it's 3/4 over 2 pi of the whole. So now we work this out and you get another fraction with a bunch of, you got a 3 on top, there's a 16 pi on top, there's a 4 on the bottom, a 2 and a 4 and a pi on the bottom. This 4 is going to end up below, because this is when you invert and multiply, this is going to be 1 over 2 pi. And so this goes out and this goes out, and this gives you 4 and this gives you 2, so you end up with 6. Same thing if you choose to avoid the formula. Finally, we have the pizza problem here. This radius of, so the trick is to understand what the problem's asking for. So normally if you were trying to split this, well, let's just use this. If you're trying to split the piece of pizza in two to feed 2 people, you would just cut it along that radius there. And that would be the easiest way to do it. Take a pizza cutter and just slice it down, and no one would have any question that was fair. What this problem, just for the sake of mathematics, is asking you to do is to give one kid this piece and the other kid this piece. So, and those kids want to have the same amount of pizza. And there's no crust. You can assume this is all pie out here and this is all pie in here, so that we eliminate the crust. So, but we want to make sure the total area of the 2 pieces is the same. So the question is, how far do I cut from this point here in order to make those 2 pieces of pizza the same size? The way to start is to look at the entire piece of slice. So the area of the slice, the easiest way to get the area of the slice is to say, well, the whole pie has a radius of 10 inches, right? It has a radius of 10 inches. The area of the whole pie then is pi times 10 squared. 100 pi r squared is the area of the entire pizza. And this slice is 1/6 of that area because it's 6 equal size slices. So that gives you 100 pi over 6, or 50 pi over 3. That's the area of the whole slice. The entire slice is 50 pi over 3. You could also use the formula again for area. Area of the slice is also 1/2 r squared theta. In this case, this theta here, this is 1/6 of 360, so that's 60 degrees, which is pi over 3 in radians. And you have to use the radian measure for these area and arc length formulas to be meaningful. So this becomes 1/2 times 10 squared times pi over 3, which is also 50 pi over 3. So no matter how you slice it, no pun intended, you're going to get that's the area of the entire piece of pizza. So that means that if the whole piece of pizza is 50 pi over 3 in area, square inches, that means you want this half to be 25 pi over 3 and this half to be 25 pi over 3. So that would result in both people getting the same area of pizza. So we look at this triangle here. So now we have a triangle, and it happens to be an equilateral triangle, if you think about it, because this angle is 60 degrees, and these two sides have to be the same. So that has to be 60, and that has to be 60. So you got an equilateral triangle here, and this is the height of the equilateral triangle, and this is its base from here to here, and this is its height, and we know the area equals 1/2 the base times the height. So we know that the area that we know the area is 25 pi over 3. That is 1/2 the base of this thing. There's the base right there. Times the height. There's the height. That's what we're supposed to find, h. All right, now it looks like we have one equation and two unknowns, b and h. So it looks like we're sunk until you realize that for an equilateral triangle, I know that this guy on the right here is a 30, 60, 90, because that's 30 and that's 60. So I know if this guy is h, and this guy right here is 1/2 b, right? This little guy here, that's just this triangle on this side. That's this triangle. This is half of base, and that's the height. And we know these guys are related by square root of 3, right? We have 30, 60, 90 right triangle. If we take the short leg and multiply it by times the square root of 3, we get the long leg, right? So if we plug this thing in here, we could get rid of the b and solve for h, which is what we're looking for. The problem is that we have to solve this thing for b first. That's the rub here, because right now it's solved for h. And so just multiply through by 2 and divide through by root 3 the entire equation. On the left side, the 2's go out. The 2 in the hat gives you 1. The root 3 over root 3 gives you 1. You're left with just b. On this side, you get 2h over root 3. That's b. And I won't rationalize it now. I'll rationalize it later. And so that means if I take this equation and this equation and put them together, I get a equals 1/2. For b, I'm going to use 2h over root 3, and for h, I'm going to use h, because that's what I'm looking for. And this I was 25, so I'm really not using this. I'm using this. Sorry, it's 25 pi over 3. So I just have to solve this for h. So put these guys together, I get an h squared. And then I'm going to multiply through by 2 and divide through by, multiply through by 2 root 3. Actually, these 2's go out, don't take that out. So I have to just multiply by root 3 and I get h squared. So I get 25 pi times root 3 over 3 equals h squared. So the number h I'm looking for is just the square root of this beast. The 5 comes out nicely from 25. Everything else ends up under the radical. Can't be simplified. So you get a radical of a radical, which is kind of nasty, but it's a legitimate number, root 3 pi over 3, and that's the best you can do. And so that's how far you would have to go from the center of the pizza. This distance right here would be 5 times the square root of the square root of 3 times pi over 3, and then you'd get equal size slices.